here put some identities. And then we also call it non-identities. So we have two sets to begin with, A and B subsets of X, and again it's equal to X to Y. Then we can consider f of the union, f of the intersection, and then as I say, f of the symmetric difference. And we can ask, would it be true, for example, that we can also consider the union of the images, and we could consider the intersection of the images, and we could consider the difference of the images. So are these equal? Do we have equality signs? And I'm sure you have probably seen that how it is. The story is, yes, here we do. So images behave very well under unions, for linear, but not under intersections. This set is in general smaller. So this could be bigger than this. However, equality holds if f is injective. And this is lemma 2.1. Here, it is the reverse situation that this set is in general on the right-hand side smaller than the set on the left-hand side. So you have this inclusion, and again, equality holds if f is injective, lemma 2.2. And it is not really that I would ask you to memorize these identities. It's not that I mean, it's not really that, you know, I want to wake you up at 3 in the morning and say, give me write down these identities. This is not an important thing here, but perhaps more important is that you are able to, within 5 or 10 minutes, to verify these identities. This is important. That you have the set theory that is making there, the set theoretical skills to verify such identities. This is important. Not that you remember them. And of course also this is something that you will be doing in exercises. There are some things in this course that you really have to remember by heart. It's very convenient to remember it by heart. And the other things that you just need to know the technique behind it. Let me then also mention that so these are relations concerning images. Pre-images behave much nicer, and this is actually useful to remember. So if you have a Ci, a family of subsets of Y, and you have C and you have D, and they're all subsets of Y, and again S goes from X to Y, then if you take the union of the Ci's and you take the pre-image using this definition over there, then this is, okay, this is right here. You can also then take the union of the individual pre-images. We can do the same thing with intersections. And intersection here. And set difference. So this is a little bit like before, but we do it even more generally because we take arbitrary families And here, the story is very nice, equality all creations. And this is something that you will be also doing in the exercises. And again, it's really something, test yourself, are you able to do it? And if you are to prove something like, let us just take one, and let us even just take this one here. You should really do it in a very mechanical way. You'd say x belongs here, if and only if, and then you go and look at the definition, x belongs there, if and only if f of x belongs, if and only if f of x belongs to the interior here. So f of x belongs here. And then we go, what does that mean? So that's related to this statement, and then it's related to this statement, and then somehow mechanically you can go one step at a time and arrive at this statement here. So this is how I want you to think about this. Okay. I will not go through these two lemmas. They are proved in the book, lemma 1 and lemma 2. And reading yourself it is not, it is good to get the idea, but it's not so crucial for the course. Then we come to this in the base, we come to the fundamental notion of counting in chapter 2. And this is something that you may or may not have seen before. My guess is that many of you have not seen it before. Definition cardinality of sets. Have you heard about cardinality of sets? Some of you have. Something like that. Consider two sets, x and y are sets. And remember, set is negative. Then we say that x and y have the same cardinality. It's a funny way of defining it. So we don't really, we do it indirectly, we don't really say what the cardinality is, we say that they have the same cardinality. If they exist, a bijection, so they exist, a bijective map F that goes from x to y. And if yes, we write a simple number sign x equal number sign y. So in some sense, number sign x means the cardinality of x is equal to the cardinality of y. And this is number sign, and number sign should somehow indicate the number of elements in a generalized way. So it is a very reasonable statement to think about it, because if you have a bijection between two sets, it means that we can pair the elements one by one. I mean, one way of looking at it is x and y. Suppose that x is a set of boys and y is a set of girls. So you can say there are equally many boys and girls if they can each go to a dance hall and dance together. So each boy dances with one girl and one girl or one boy. So you can match them completely. If this is possible, then there are equally many boys and girls. Now, otherwise, there will be some boys based on the baby song and some girls based on the baby. But this is the ultimate test. You have some boys and some girls, and they all go and dance together so that each make a couple. And this is precisely what this says, because the bijection is the map says that which story should dance with this girl. This is what bijection does. So for each story, it's x, it assigns a value y. And this value 1 means that two different boroids stand to two different curves. It is on to, that means that every curve stands to the boroid. So this is a perfect maximum. So therefore this is a very reasonable thing. We also say that x has smaller cardinality than y if there exists injective map f from x to y. And if this is the case, we write cardinality of x less equal to cardinality of y. And again, if you look at the Borel picture, then if x is a set of boroids and y is a set of curves, an injective map would be a way so that each boroid gets to dance with one curve, and two different boroids dance with two different curves. And the only thing that goes wrong is that there are perhaps some curves that are not invited to dance. So there are some curves that don't, there are some curves sitting on the bench. And if this is the case, then there are more curves involved. So it's really, it's really a very natural way of defining the size of sets. And seemingly, very profound and deep. However, if you study cardinality, the study of cardinality can be almost infinitely arbitrary and key. There are very hard questions concerning cardinality, and we should even encounter very quickly one of them. Then we finally say that we say cardinality of x is strictly less than cardinality of y if cardinality of x is less equal to y and they're different. So this is the usual way of strict equality. Okay. So this is the definition. Although it may at this point I say it backwards, but let's try to go a bit further. And let me also say that we are not going into the depth of the theory of set theory. We're only really going to pick out a few things that we need. And the big, huge, profound questions we need to other people, and we see them later. So we're only here going to scratch the surface. Okay. So let us take some definitions. We have some sets already lying around. We have the empty set, and the cardinality of the empty set we know